Okay, in this video, I want to explain what E is, the constant E. So E is defined, E is a constant, it's a number, a real number, and it's defined like this. So you take this sequence, you take 1, okay, and then you take 1 plus 1 over 1 to the first power, and that's 2. Then you take 1 plus 1 half and then square it. That's going to be 1 plus 1 over 2 is 3 over 2. That squared is 9/4. So that's 2.25. And then you take 1 plus 1/3 cubed, and that's going to be 4/3 cubed. That's 64 over 27. And you continue. So you get the nth term of the sequence is 1 plus 1 over n raised to the nth power. Well, starting from n equals 0. Well, okay, if n is bigger than or equal to 2, the nth term of the sequence is this. So I'll call this A2, and then I'll call this A1. There you go. So AN is equal to 1 plus 1 over n to the nth power. So this is actually true if n is greater than or equal to 1, right? You just don't have this issue when n is 0. If n is 0, then, okay, you can't have 1 over 0. So if n is greater than or equal to 1, you have this sequence whose nth term is 1 plus 1 over n raised to the nth power. Now when you look at these numbers, 1, 2, 2.25, 64 over 27, they appear to be approaching a number. And it turns out that they in fact do approach a number, and that number is called E. So as n increases forever without bound, AN approaches a number, and that number is called E. And E is about 2.7. Now what is the significance of E? Well, it turns out that it's used in exponential functions. So if you have an exponential function, let's just review what that is. That's a function y equals a to the x power, where a is positive. Now if you set a equal to E, actually a should be greater than, let's see. Yeah, I guess a shouldn't be equal to 1, right? Because if a is 1, then it's just 1. So I guess we should say that a is not equal to 1. And if a is e, then y equals e to the x has a nice property. And it won't make sense unless you take calculus, but it turns out that the derivative of e to the x is just e to the x. In general, the derivative of a to the x is not a to the x. If y is equal to a to the x, then y prime is equal to a to the x times the natural log of a. So you have this constant out in front, which is kind of annoying. It's this constant that's being multiplied by a to the x. And so that's why e is significant, because it's sort of like a normalizing factor. Okay. So let's look at e to the x. Well, in general, if you have let's look at these properties of exponents. So in general, if one of the properties of exponents is that properties of exponents. So one of them is this property that when you have a to the x plus y, this is equal to a to the x times a to the yth power. So for instance, if you know, if a is 3, okay, and x is 2 and y is 4, so this would be 3 to the 6th power, and this is in fact 3 squared times 3 to the 4th power, because you're just multiplying, because both of these are 3 times itself. You have 6 3's and you multiply them together. Okay, but it turns out to be true for all real numbers, not just integers. So a is positive, right? So a is a positive number here, and x and y are real numbers. And of course, if it's true for any positive number, in particular, it's true for e. So e to the x plus y is just e to the x times e to the y. So that's one property of exponents. Another property of exponents is that if you have a to the x raised to the yth power, that's a to the x times y. And again, you can look at it with specific numbers. If a is 3 and x is 2 and y is 4, then the left-hand side is just 3 squared to the 4th power, and that's 3 squared times 3 squared times 3 squared times 3 squared. When you have 4 of them, you multiply them together, and each of these 3 squareds is 3 times 3. So you have 3 times 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 3, and how many 3's are you multiplying together? 8. So you see that in this specific example, the property is true, but the property is true in general. Okay, x and y don't have to be integers, they can just be any real numbers. Alright, and if you look at the graph, well, we have graphs of a to the x, but let's just look at the graph of e to the x, for example. So if x is 0, e to the 0 is 1, right? If I plug in x equals 1, I get e. That's like 2 point something. If I plug in 2, I get e squared. That's somewhere between 4 and 9. And when you graph all of them, you get this graph. It approaches 0 as x decreases and is negative and just keeps getting more and more negative. The y values approach 0, and as x is positive and gets bigger and bigger and bigger and increases without bound, the y values do the same thing. And it turns out that this function is invertible. There's no way you can have two x's that give the same y value. This is an increasing function, and it has an inverse, and that inverse is called the natural log function. So to graph the inverse, you reflect it across the line y equals x, because you're just switching the x and y coordinates. So this function is e to the x, and when you flip it across, you get this other function called the natural log. This y equals natural log of x. And the natural log of x is only defined when x is positive. Right? There's nothing out here. Okay. When x is negative. And that's because the outputs of the exponential function are always positive. And so we get stuff like the natural log of 1, well, the natural log of 0 is undefined because there's nothing you can raise e to get 0. What's the natural log of 1? It's 0 because e to the 0 is 1. And similarly, the natural log of e is 1 because e to the first power is e. And the natural log of e squared is 2 because you have to raise e to the second power to get e squared. And in general, right, natural log of e to the x is just x. That's just by the definition of an inverse function. And let's look at some properties of the natural log then. So, for instance, if you have the natural log of a times b, where a and b are positive numbers, well, if a and b are a positive number, they're e raised to something. The point is that this exponential function, the outputs cover all the positive numbers. So if I have a positive number, it's e raised to some number. That turns out to be a theorem. So since a is positive, a has the form e to the something. Let's say e to the cd. A equals e to the c, for some real number c. And likewise, since b is positive, b is equal to e to the d for some real number d. So therefore, a times b is e to the c times e to the d, and this is equal to e to the power c plus d. So the natural log of a times b is the natural log of e to the c plus d. And now, by definition, this is equal to c plus d. Well, if a is equal to e to the c, that's the same as saying that c is the natural log of a. Yes, that's exactly what it means. Because c is what I have to raise e to get a. And the fact that b is e to the d tells you that d is the natural log of b. So therefore, c plus d is just the natural log of a plus the natural log of b. So we just discovered that the natural log of a times b is the sum of the natural logs. So that's one property of natural logs. So this is if a and b are positive. And this is a very important property of natural logs. It's the main property you'll end up using in calculus. So you'll be using this fact and also these facts, right? Just that, this natural log of e to the x is x, and this property of natural logs. And also if you have the natural log of a to the bth power, this is equal to b times the natural log of a if a is positive. Otherwise, natural log of a is undefined. Why is this true? So again, since a is a positive number, we can write it as e to something. So let's say e to the c power for some real number c. So a to the bth power is just e to the c raised to the bth power, and that is equal to e to the cb. So the natural log of a to the bth power is the natural log of e to the cb power, which is equal to c times b. But c is the natural log of a. So this is b times the natural log of a. So that proves this fact. And this is also used in calculus, for instance in logarithmic differentiation. So at the very least, it's important to know what natural log is. It's the inverse function of e to the x. You need to know what e is. And some basic values, right? E to the 0 is 1, so therefore natural log of 1 is 0. You should know the natural log of e to the x is x. And you should know these basic properties of natural logs, these two, and why they're true. I mean, on a test you probably won't be asked why is it true, but you should be able to understand the reasoning and figure out why. Because you can just write a as e to some power and then use these properties of exponents. See here we use the property of exponents, and you saw how these translate to properties of natural logs. And here we use this property of exponents, and this translates to this property of natural logs. It led to that property. So the properties of natural logs are related to the properties of exponents, and you should understand how all of this works. Okay, even if you won't be asked this on a test. Okay, so that's just the basic review of e, exponents, and natural logs.